Thank you. And I'd like to express my thanks to the organizers for inviting me to this workshop, this semester. I did enjoy a lot the workshop so far, maybe the current talk, but I'm sure I will enjoy again. The title of my talk is this is the journey with Fernand Pelletier. What we are doing in this work is to basically to revisit an old problem related to the integrability of Banach-Lie algebras, more exactly to the existence of Banach-Lie algebras that do not arise from Lie groups. And we try to offer a class of groups that are, as we hope, close to the Lie groups, and that still allow us to recover all the Banach-Lie algebras. And I will start with by recalling an example that is quite old, but it does show a bit the difficulties that appear. It's an example due to Douady and Lazare. The framework of the example is given by a Hilbert space that is separable infinite dimensional complex. And we consider the Lie algebra of all skew adjoint bounded linear operators this is really a Banach-Lie algebra when we endow it with norm topology, and then for an arbitrary irrational number, we define the following one-dimensional Lie algebra IT times 1. This is the identity operator on H, IT theta, where T is an arbitrary real number. This is actually an ideal, as it is contained in the center of U of H cross U of H. And we consider then, because this is a closed ideal here, we can consider the quotient this will be again a Banach-Lie algebra, and I should emphasize here, for reasons to be explained later, non-separable. And then the remark of Douady and Lazare is that for every Banach-Lie group, its Lie algebra is not isomorphic to Beltita. In other words, this is a class of Lie algebras, Banach-Lie algebras that cannot be obtained from Lie groups. And at this point, several questions can arise. For instance, several points of view can be adopted. For instance, either we consider these algebras to be pathological objects and forget about them, but maybe it's interesting still to enlarge the class of Lie groups in order to be able to obtain even these algebras as the Lie algebras of some groups. Since we insist on having a kind of Lie group, so a group with an differentiable structure, we insist on working with groups. The only thing we can do is to weaken the axioms for the structure of smooth manifold that our groups.
What is a non-separable Banach space? It means there is no countable dense subset?
Yes.
Like in the Hilbert case?
Yes. Okay. This space is separable, but the bounded operators on it are not separable.
I don't know the notions in Banach case.
What notion? Well, for instance, the explanation is that if we fix an orthogonal base and we consider the diagonal operator.
Yeah, it's clear. In Hilbert case, it's clear. It was just a question.
I mean, this is probably a topological case. We could have a countable dense subset or not.
Maybe.
I mean, I will explain later why I insist on separability. So I was saying that we are trying to figure out a structure, weakening of the structure of smooth manifolds that would allow us to recover all the Banach Lie algebras through a suitable Lie functor. This kind of Lie theory for groups beyond Lie groups is actually a rather old topic. Maybe it goes back to Hilbert's fifth problem. So I will write here, just for the sake of history, these two names. VM Glushkov and R. Lashov, who simultaneously, separately, but in the same year, 1957, proved that every locally compact group has a Lie algebra. So one direction was to try to understand a bit or to carry out Lie theory for topological groups. Another direction that is closer to what we are going to do is to actually kind of forget about the topology and focus only on the smooth structure. And this is the direction that was pioneered among other persons by Raymond Barre. In 1973, introduced the notion of Q group, manifold and Q group, where Q comes from quotient, because these groups are in particular quotients of Lie groups by subgroups that are not necessarily closed. So these groups are a kind of Lie groups, and he developed Lie theory to a quite a large extent for this kind of groups. What we are going to do is to work in some sense in the same spirit, except that here he worked only with finite, in some sense, finite dimensional manifolds, although he had a student, Michel Plaisant, who in 80 introduced Banach Q groups. Her motivation was exactly to address this non-integrability problem, but she managed. Her attempt was basically for separable Banach spaces, and that was emphasized here, that although her theory was not complete even in that case, but still worked only for separable spaces. And so we are trying actually to kind of complete many years later this program. And in order to make it applicable to this, the very first example of non-integrable Banach algebra. And a bit of terminology before I go further. Whenever I will say smooth manifold, I actually mean what is usually called the smooth Banach manifold. That is manifolds modeled on Banach spaces. And in particular, Lie group in the Bourbaki style would mean actually real Banach Lie group. Just in order to mention so many times Banach, but all the Lie groups manifolds will be modeled on Banach spaces. And the structure that we propose to endow the groups with in order to recover the general Banach algebras, we call them H structures, where this H comes from the word homogeneous, because as we will see, they satisfy a kind of homogeneity property. But in order to motivate them, I will start by a remark on smooth manifolds in that sense. Namely, if S is a smooth manifold, with an atlas where they are actually not charts, but rather parameterizations, but I still call it an atlas. U sub I is open in some Banach space, and the V sub I is open in our manifold. So we take just any atlas and we do the following following construction. We consider the disjoint union of all these maps. Firstly, its domain will be the disjoint union of all the charts, of all domains of parameterizations. And we define pi with values into S by the condition that pi of x is just pi sub I of x if x belongs to U sub I. So it's a kind of direct sum of these maps. And this is a map that has the following properties. Firstly, it is surjective because this is an atlas, and it is only locally injective. And secondly, if we have 2 points x and x prime in this joint union that have the same value, then there exists a map H from U to U prime, where we have the following additional properties. U and U prime are open neighborhoods of x and x prime. You will recognize will be given actually by, it will be a change of variables between the corresponding parameterizations. So x belongs to U, M, x prime, M. Secondly, pi composed with H equal to pi restricted to U. In other words, this map is compatible with this pi in the sense that it preserves the fibers. And of course, H should take the point x to x prime. And moreover, the germ x of H is uniquely determined by the above conditions. Why is that? Because, of course, these maps are invertible. So, I mean, it's just a trivial way of formulating the hypothesis that this is an atlas. And we will take this as the second condition as the definition of our H structures. And we'll see that this will do very well.
It's not a covering, right? It's the different union of...
Not us, yes. So they do cover. I mean, this V sub H is the union of this V sub H.
So if you have two... Phi x is defined like phi x.
So
if x belongs to two of these...
We have a manifold covered by some domain of charge.
Yeah, so if next is in the intersection, it has to be the same value.
What is the disjoint sum?
This is a highly non-connected manifold, but exactly this is the idea that it is non-connected, but it is it should be thought of as having a simpler structure than this. This is like an open, a disjoint union of some walls. That is the manifold, and we try to use it in order to understand the general manifold.
So S might be not Hausdorff.
It's a good question, but we work here only with Hausdorff manifold. But I will explain later why it is. I think it is very good at this point, but I will explain later that it will not play a central role. And then the definition that I wish to make is the following one. We have a map just like this, because that is our introductory notation onto S. M is a smooth manifold. Or maybe I should. And we introduce a notation for the locally defined diffeomorphisms that satisfy this condition. Mainly we denote them by gamma of pi. This is a pseudogroup on M, and we select a sub-pseudogroup of this. And then with this data, we say that the quadruple M pi gamma on S is on H atlas, even though if pi is surjective, and this condition here is satisfied. But with H in gamma. So we fix the pseudogroup of local diffeomorphisms where we allow changes of variables in some sense. And we drop the condition that it should be locally injective. This is the difference between H manifold and smooth manifolds. It's that our atlases are not locally diffuse. And okay, now we do the usual stuff. We define an H manifold structure. It's just an equivalence class. Okay, atlases. But I won't say what I precisely what I mean by equivalence of atlases because we don't need it, but just to say that it is meant in the sense of André Effiger, who introduced such a notion for finite-dimensional manifolds. So equivalence a la André. But really we don't need this because our most concern will be all the time to prove that a certain projective map is an H atlas with respect to a suitable group. So these are the objects of our category, and the morphisms are defined like this. If we have two atlases and two manifolds, I don't know, is this too small? Can you see something? So if we have a map F between two H manifolds, we want to say what it means F to be smooth in this sense. So F is H smooth if for any point S sub I is capital S sub I with F sub 1 equal to S sub 2. There exists X sub 1 over, so here is, and we want X sub 1 here. And some open neighborhoods of these points in the corresponding manifold, so these two are closed. And there exists a smooth lift of F to this. For which this diagram is commutative. So phi 2 composed with F hat is F composed with phi 1 restricted to U1. And with this, in the same spirit, we define H immersion, H submersion, H map by the condition that there should be such a lift that has the corresponding properties. And of course, we prove that with respect to this equivalence of atlases, it doesn't matter what atlas we choose. And in the end, I can say by now that the group objects in this category defined by these objects and these morphisms will suffice to recover all the Banach algebra. But in order to be more specific, of course, we need some additional details. Before going further, I will say an example, a couple of examples actually, since this condition may seem difficult to check, but the idea for the example is that there is a more restrictive notion, namely the one introduced by Raymond Barre of two groups. That is easier to check.
Namely, Daniel, actually I was a little bit lost. You assume that S is a topological space and pi is surjective or more?
Yes. S is just a set without any structure.
It's just a set, but pi is surjective.
Yes. Yes, pi is. So we just have, okay, maybe I should say now this notion is modeled by the study of leaf space, because that also explains the title. Leaf spaces of foliation without holonomy. This uniqueness condition here expresses that isotropy of the holonomy group or pseudogroup is zero. So if you wish, you can think of this as the leaf space of a certain foliation here. I will later. So this is just a set without any structure, and we try to organize it somehow as a kind of differentiable space. And Raymond Barre introduced the following notion of Q atlas. For finite-dimensional manifolds by the following conditions. Firstly, that pi should be surjective. And the second condition that implies, the second is are without uniqueness. Meaning that whenever we have 2 points that are mapped to the same, there exists a diffeomorphism, but we say nothing about uniqueness. You see here, uniqueness follows because our charts are invertible. But as I said, the main problem here is that such maps are not locally injective. And the third that ensures uniqueness is that for any F1, F2 maps, smooth maps from T to M, from T to M, satisfying the condition that pi composed with F1 is pi composed with F2. Smooth, meaning in particular that this T is a manifold. Then the set of points T where they coincide is open. So this is the condition that he imposed. And that is really, I mean, allow us to check that many things are Q atlases. But the basic example for us is that whenever we have a group action on a manifold where M is smooth and the group is countable, the quotient map is a Q atlas. No, nothing. Just any. In particular, if you wish a tracking example, the quotient of the real number by the subgroup of rational numbers is always the Q manifold. As I said, we are looking for objects more general than smooth manifolds.
I don't remember what is Aleph 0 is. This is a count. This is Q or R?
Which?
This should be Aleph 0 or what?
Yes, that means the group is countable.
Countable, yeah.
Countable, yes.
Sorry, I'm confused. So what if I took Z2 action on R with the stabilizer at 0? Then wouldn't that be wouldn't F1 be the real line? And Z2, X goes to minus X?
X goes to minus X.
And that's
the action of the cycling group.
Yeah. Yes. And then if F1 is the identity and F2 is negative the identity. But I think if it's a free action, then okay. I'm sorry.
0 is a fixed point.
Yeah, the action of for Z equals to D2.
But which space is the half line? Including 0.
But sorry, maybe I can ask. This was a bad time to ask.
The points where they coincide.
It's okay.
You mean the equal?
It's not
But this, they coincide only 0.
I think that would be an action R star, not an R with a billion group structure.
I don't know, I think I will be more,
It is just the half line, including 0, and it's an orbifold. And an orbifold should be Q thing.
they are the action of a finite group.
Orb is an orbifold.
Yes, and for them, this condition is not satisfied.
It is. Is it not?
Sorry, I think this is.
So, but Peter, the difference to say that this is a Q manifold and to say that this map is a Q atlas. Maybe this map is not a Q atlas, but of course the quotient should be a Q manifold. Maybe this is not the right. I mean, it looks like what Grothendieck does with his CFs of étal maps in the Grothendieck topology. Grothendieck allowed covering étal maps, finite coverings.
Yes, an atlas should be thought of as I mean, this is somehow by definition. And yes, I forgot to say this. I mean, I will think more about that. The point is that every Q atlas, I mean, if we have a Q atlas, then it is an H atlas, but with the maximal pseudogroup here. So this is what the point is, that in this case we have a kind of a maximal pseudogroup. We don't need to select one. And this without uniqueness, meaning that although without any condition on it, just okay, and so now how we can build such structures? As our main purpose here is to organize a quotient quotients of Lie groups by non-closed subgroups as to organize them and as H groups in this sense. A technical theorem that we need, it's slightly more general than what we need, but okay. If M is a C0 paracompact, in fact, it's a version of the Godeman theorem, but for the structure that we need, the Godeman theorem on quotients of smooth manifolds. And if R is an equivalence relation, we consider the corresponding Cartesian projections and we make the following assumptions. Firstly, that R should be endowed with a smooth manifold structure, such that firstly the inclusion should be an immersion. And secondly, that these two projections, two maps, are submersions with connected fibers. Then the assertion is that firstly, the equivalence classes of R give a foliation of M. That is why we require the fibers to be connected in order to be able to say that the equivalence classes are connected, so they can be R reliefs. And secondly, the quotient is an H manifold, and the quotient map is an H submersion. So in some sense, this is the main tool to produce manifold structures on the quotient spaces. And we actually are interested only in the case when M is, in quotients of Lie groups by immersed subgroups. So I will state this corollary. Yes?
You say immersion, you mean in the sense of Bourbaki with complement?
Yes, so the differential should be an operator injective with a closed range and with a complement. And maybe I should explain a bit why we need paracompactness. We need paracompactness in order to, the method to construct this H manifold structure is to look at at the transversal structure in some sense of what should be eventually the leaf of this foliation. And okay, in order to arrange a bit better the various coverings, we need to refine them at some point. In particular, if the manifold is metrizable, we have that hypothesis satisfied. The corollary for Lie groups is like this. If G is a Lie group and K in G is a connected map subgroup. So in particular, it has a structure of Lie group for which the inclusion is an immersion. And if Q is the quotient map, then the following facts hold. Firstly, G over K. I mean, we consider the equivalence relation given by congruence modulo K. G over K is an H manifold. Q is an H submersion. And the kernel of the tangent map of Q. Well, I didn't have time to explain this, but I hope I said, at least in passing, that we can define the tangent spaces and the tangent maps of, basically the tangent functor on this category and H manifolds, and it still takes values in the category of H manifolds. So it makes sense what we write here, although Q is not a smooth map in this case. And if K is an initial subgroup, then this G over K is actually a Q manifold in the sense of bar. Initial subgroup in the sense that whenever you have a smooth mapping into G with values in K, it will be smooth into K. In fact, it is for this property that this separability assumption is needed in the theory of Q manifolds and Q groups. And now here before continuing, I should say a bit, because we keep talking about H submersions, but when this map is really an H atlas, under the hypothesis that K is a normal subgroup, then Q is atlas if and only if K is pseudo-discrete. In the following sense, if gamma is a smooth mapping from an open interval in the real line with values into G, and so this is, and gamma of I is contained in K, then this is constant, gamma is constant. Here, if K is countable, then this is coherent with what I said before, because the map, this condition is clearly satisfied. But the fact is that, I mean, countable group satisfy this. The fact is that if G has dimension strictly larger than 1, then one can even find pseudo-discrete subgroups that are connected. A few examples is a pseudo-discrete. But also there exist connected in R2. The proof that I know assumes the continuum hypothesis, and so it is not constructive. I cannot show you exactly an example. It means that we compare certain the cardinalities of certain sets of subsets, and I should add somewhere that actually this is, let's say, interesting. I mean, it's more interesting whenever the dimension of this space is smaller. Before, when we replace R2 by real Banach space, such examples were known before, I mean, a long time ago. I'll recall it, this is right here. So if G is LP of the interval 0, 1 with real values, and it contains the functions that are integer valued almost everywhere, then this K is pseudo-discrete. It's connected and pseudo-discrete. An example that goes back to the work of Karl-Heinrich Hoffmann. I think in the early 70s.
K is not necessarily closed. It is not
no. So K is just I mean K is an immersive sum. In the setting of the Broglio's corollary. In the corollary, no, it is not necessarily closed.
And it's not normal.
Well, no, it is not normal. This is just a manifold.
So in this case, you say that the relation given by the function of K is
satisfies these conditions.
So it's a submanifold.
Yes.
I don't see the complement.
No, I mean it's the usual trick that we use this map psi from this cross this G. This takes to the graph of the equivalent relation model. Okay.
Yes, right, but I don't see that you use a Bourbaki definition of immersion with complement, right? So there should be a complement to the tangent space of the graph.
Yes, so this set is clearly complemented and so on, unimmersed. G cross K, because K is in G. Then G cross K is also immersed into G cross G. Okay. And because psi is a diffeomorphism, it will take this immersed to another immersed manifold. Okay, so and now I will state final facts. It is because really it's only the special case of the theorem that we need. We will conclude by this. H group is a so-called group object in the category of H manifolds. So a group structure on an H manifold for which the structural map is smooth. And then the first theorem is that there is a well-defined Lie functor from H manifolds to, I will write here Banach Lie algebras, real Banach Lie algebras. Yes. We just, as usual, we take the tangent space that makes sense, and the Lie bracket is defined using the left invariant vector fields or right invariant vector fields, so in the usual way. And but the main point is that this is surjective. This is a functor, and Lie is surjective. So this would be. And maybe I have a couple of minutes to explain just a little bit the idea of the subjectivity. So we take any real just to emphasize that we work with Banach algebras, and it is known that there exists G tilde with a surjective map Q from in examples such as this one, they already appear as a quotient. In general, a method to construct such an algebra for which that is of the form Lie of some Lie group. I mean that every real Banach Lie algebra is a quotient of a certain algebra that is integrable. If the algebra is not of that form a priori, then an example of method due to Wiercichowski is to use the path functor that also appeared in the talk given by Cornelia, is that we consider the path functor consisting of all continuous maps from the interval 0, 1 to G that vanish in 0, and this will do. From this, the evaluation at 1. So Wiercichowski proved that this is always integrable, and so the evaluation map gives us such a quotient. And and then we use this to organize the algebra as we look at the kernel of this map. Try to hurry up, it's not a good idea. So we look at the kernel. This is an exact sequence. And moreover, yes, I forgot to say, we also require this to be linearly split, which holds true for this construction of the path functor. And then we have the group that will play the group of the role of this group. We integrate the Lie algebra to an immersed and connected subgroup. and then we take the quotient, and it turns out that the corresponding quotient will be isomorphic to our Lie algebra. But this, what we obtain here is just an H group, is not a real Lie group. So in this way, an arbitrary Lie algebra is obtained as the Lie algebra of an H group. If it happens that G really comes from a certain Lie group, it is already integrable, then what we obtain by this construction is actually, one can prove that it is the universal covering group of its corresponding Lie group. So, I think I will stop here, but just, I mean, this can be regarded, developed further in maybe two directions at least. Firstly, to try to understand if this is really, or in some sense, minimal in some sense category of groups. Or if you obtain here a subject reduction. And maybe secondly, I don't know, to understand or to better develop the theory of such groups. Perhaps even the representation theory makes sense anyway. So thank you.